validity of this kind of approach, one has to show that the partition function does not vanish in a large enough region. But how does one use this for an algorithm? So basically you want to use a Taylor series expansion at 0. So you want to compute these coefficients, which basically correspond to the first k derivatives of log z, which can in turn be computed from the first k derivatives of z at 0. So you are also to k point correlation. So essentially you try to do two things. You first try to prove that this radius r up to which the partition function does not vanish, and hence you have nice convergence of the Taylor series is large. And then you want to somehow compute these coefficients. You can sort of so it turns out that you only need to go up to k about log n. So just by brute forcing the derivative computation, one gets n to the log n algorithm. That's what Barvinok initially had. And then of course the harder thing is to show how to compute this r. How do you prove that there are no zeros after the radius r? But this, for various reasons, some of which will come to later in the talk, has been a well-studied problem for several classes of partition functions. For example, for the independent set polynomial, it's known that it's not equal to 0 as long as the lambda is less than about 1 over ed in absolute value. So in the disk of radius 1 over ed, it's not 0. This is interesting in combinatorics and this theorem, which we'll mention later in more detail, says that for the Ising partition functions, for the ferromagnetic Ising partition function, so beta less than 1 corresponds to, remember, the ferromagnetic case, the partition function zeros all lie on the unit circle in the complex plane. So this sounds, at least the first time I saw this 5-6 years ago, it was extremely surprising that how, I mean, this thing that here's you can take any graph, if it's the ferromagnetic Ising model, all the zeros will lie on this one circle, and the circle is fixed, it does not depend upon the graph. So these kind of results do give you some information about where the partition function is, where the Taylor series is going to be converted, and you have to use that with this to get these algorithms. So the general thing here would be to do two things. One would be to somehow have an algorithm for computing these coefficients, and the other would be to show where z is 0 free. And this n to the log n, Patel and Rex gave techniques to take many of the applications that Barvinok earlier had, and to make them polynomial and bounded degree graphs. So this did not work for the Ising model, but we'll see that that can be fixed, and one can come up with algorithms again to remove this quasi-polynomial dependence and compute these coefficients polynomial time for the Ising model. So even though these original things didn't work. Okay. So yeah. So let's let me just mention the Li and Yang result again, because that sort of is just nice. So and also tells you how you get the result for Ising model. So just to recall, so for the ferromagnetic Ising model, so beta is between 0 and 1. The 0 is the partition function viewed as a polynomial in lambda, this parameter. They all lie on the unit circle. It does not depend upon which graph you are on or what the degree of the graph is. So this partition function is 0 free except on the unit circle. So the Taylor series of log z at 0 has radius of convergence at least 1. In fact, it's exactly 1. There are points of singularity on that. Okay. So yeah. So for us, this is the result that plays the part of this question about where is the series converging, and then of course these coefficients are to be computed. But using that, one can get the FP task for the Ising partition function I earlier told you about. But as I said, we can also generalize this to hypergraph. So one can get in this case. So even instead of edges, you have hyper edges. So higher order interactions, one can still get results. But not throughout the ferromagnetic Ising regime. It now depends upon what the order of the interaction is, and that is because in this case you don't have the nice Li-Yang kind of result which showed that you have zeros lying on the unit circle everywhere in the whole parameter space. Here you do get that Li-Yang type result, but probably it only works for some smaller range of beta. If you go beyond this beta, you can construct graphs where the zeros do not lie on the unit circle, and so this range of beta is tight. And so wherever you are in this range, one can again approximate the partition function even on hypergraph. fixed maximum degree and fixed maximum edge type k. So this is interesting because that, as I said earlier, the Markov chain approach for sampling from the Ising model is based on translation into something called high temperature expansion in physics. And this is a commutatorial transformation of the model, which just does not seem to work. So the analysis of the Markov chain just does not seem to work as soon as you change edges to hyper edge. So it's very commutatorial in nature, and many of these things just go away. But this method does not seem to have this. Yeah. Yes, but yes, yeah, but you're still going in the complex plane to compute it. No, but that's what I said. So Markov chain Monte Carlo doesn't. Yeah. Yeah, but yeah, so then you have to yeah, so it's like there first of all 2 to the n configurations, and some of them have very different weights. So you have to, so anything that you do here seems to reduce to showing that yes, some cases, yeah, but in general there has to be some place to start from, and so so you can do things like if you have you can change parameters using importance sampling. That has been studied very well. So you have a sampler for some parameter value, and you use the importance sampling kind of idea to sample from a slightly different parameter. So, but this error builds up. So you can go so far, and yeah. Okay. Yes. But this, so one has to again prove this kind of Liang theorem for hypergraph. And then you can also generalize it to general interactions. So this hypergraph thing was still like a single beta and a single lambda, but you can go to the case where you have different edge interactions. So each hyper edge has its own interaction and still get some results. I won't go into the details. But again, the nice thing is that all these things seem, it's not even clear how to start with Markov and Monte Carlo. Here you can. So yeah, so the algorithm I have already outlined what it does. So the first thing is essentially just Barwinock's idea or Taylor's idea that you have the Taylor expansion. You know by your Liang theorem, either the original Liang theorem or this new theorem for hypergraphs, that the series does converge all the way up to radius 1. So now you want to compute a certain number of terms in the Taylor series. So you have to have an algorithm for computing it quickly. So to compute the k term in the Taylor series, you will typically need to compute a k-wise correlation, as I said earlier. So that will be n to the k time. That's not how much time you want to expend, because then it will be a quasi-polynomial time algorithm. So as I said, so Patel and Rex already had ideas to improve this dependence, remove this dependence upon n. And the main idea there was that they didn't need to go over all subsets of vertices, all possible k-wise correlations, but only correlations for connected subgraphs. And those have so the number of connected subgraphs of a particular size in a bounded degree graph is not n to the k, but d to the k, where d is a degree. If you're looking at a connected subgraph of size k, there are only n times d to the k many rather than n to the k many. And that's where they got the improvement. This construction, however, doesn't work for the Ising model or for hypergraph Ising model. So, but what one can do is, one can generalize this and come up with different notions, which using which one can do a similar kind of analysis to show that when the hypergraph or graph is a bounded size, you can still compute all the coefficients you need in time that is only running in d to the k, where d is the degree bound rather than n to the k. And k, the number of terms that you have to compute is about log n, and that's where you get the polynomial time. Okay, so summary of things so far is that the stability theory, which is the study of zero-free regions of polynomials, this has a long history, especially in electrical engineering, started in the late 1800s, but has since become very important in probability theory, especially in the recent years, but also in physics. So this whole field of studying zero-free regions of polynomials seems to be a new primitive for doing this approximate approximate counting kind of problem. There's some combinatorics involved about counting these structures, and then you want us to prove a zero freeness result, and you get out of that an algorithm for sampling from the. So not everything is nice. So I'll come to that later. But let me also mention a few other applications of these kind of approaches. So I talked about the independent set model earlier, and it turns out that So far we are only interested in positive lambda, positive beta, and so on. But in the independent set polynomial, it turns out that even the negative case. So here, putting a complex or negative lambda is also interesting, and it's interesting because of its connection to something called the Lowash local lemma. I don't know. How much time do I have? About 5 minutes? Huh? Okay, 5 minutes. Okay. Okay, so then maybe I won't go into that. So yeah, so there's a yeah. So if you want, you can read it. There's a fundamental class. Not it's called the Lowash local lemma, but there's in fact many Lowash local lemmas, which are conditions on showing that a certain class of events do not happen altogether. It's like they're improvements upon the union bound in some sense, and they are intimately related with the independence set polynomial with negative lambda, and one can use these results on so one can use results on zero freeness of the independent set polynomial proved by Scherer to get some bounds there. But it turns out that one can even do correlation decay, which does not even make any sense because there's no distribution, there's no correlation, and so on with complex values. But one can use some kind of correlation decay as well to approximate that in this setting using similar to the ideas in White and earlier. And somehow there's some kind of a speed advantage that correlation decay seems to have. I'll come back to this in a minute. This leads to some new kind of algorithm for something called the algorithmic Lowash local, which is to find a configuration of those events where all of them don't fail. So this seems interesting. I can talk more about this offline, but so one aside I wanted to say is why would Li and Yang have proven their theorem about complexities of partition function? Of course, the physical setting is only positive beta, positive lambda. Even the independent set, I said that there is an application to Lowash local lemma, but that comes much later. Earlier, it's not there. And so why would you be interested in complex zeros of a physical partition function? So this has to do with this fact that the log of the partition function, the derivatives of the log of the partition functions, the way the Gibbs distribution is defined in such a way that its derivatives correspond to natural observables. So for example, for the easing model, one can do this simple exercise to see that the derivative of the log with respect to lambda is precisely the average number of plus vertices. It's the average magnetization. It measures a natural observable in the system. And so singularities in log z, or non-analyticity of log z, corresponds to phase transition. So such an observable will have a discontinuity only if log z has some non-analyticity. And so then one wants to study where one can be sure that there will be no phase transition. And this is the setting in which in Yang were interested. So they showed that log z is essentially analytic everywhere except for so if you take any point on their main theorem is that the main sort of general thing here is that if you have a point on the real line, so that there's a neighborhood in the complex plane around that point in which the partition function does not vanish, so that log z is analytic, then at that point cannot be a phase transition point. Things cannot be non-analytic near that point. Okay. So what Li and Yang theorem says in that language is that the only place on the real line where zeros can come arbitrarily close to the real line is the point lambda equal to 1. So that's a zero field case. At every other point, zeros remain far away from the real line, and hence you have no phase transition at any point except for this lambda equal to 1. Okay. So recently we have also been able to go the other way. So far we were trying to describe algorithms for counting problems. It turns out that ideas that you have in analyzing these algorithms can also be used to prove these freeness results, which as I said are of interest in physics, or at least statistical physics, for modeling phase transitions. So one can show, for example, so the Li-Yang theorem was looking at zeros in the lambda parameter. The question of studying zero in the beta parameter for fixed lambda has also been asked by Fisher in the 1960s, but there much less is known, especially for general. So we showed that one can use correlation decay to prove some results about zero freeness in these zeros. So one can show that when you're in the correlation decay regime, there are no zeros around in the neighborhood of the correlation decay regime. So basically, you have no phase transitions of this kind, of the non-analyticity of the free energy kind, at points that are in the correlation decay regime. So, and the proof goes by showing that there are no zeros. Okay, so yes, so just some so just the final summary is that so we have this new primitive that seems to be there about zeros of polynomials, and it seems to work even in cases where MCMC or correlation decay don't work or are not known to work, or one doesn't even know how to start designing such an algorithm. But there is a catch, and this is something that I was hiding all through, that when you can prove that MCMC works, so the techniques for proving that Markov chain Monte Carlo works are usually such that once you have done with your proof and everything works, then the runtime guarantee you get looks like this, that there's a polynomial in n, so n is the number of nodes in the graph, times some function of the parameters of the model. Whereas for these methods, both correlation decay and zeros of polynomials, the runtime looks like n raised to some function of the parameter. Okay, so this is bad. I mean, so here there's a degree of the polynomial is fixed. It's usually 1 or 2 many Markov chain algorithm. But of course, you might not be able to prove that bound. But the techniques are so that if you are able to prove any bound, the bound usually looks like this. For these methods, it's always the dependence is always on the parameter, is on this. It's not, in the language of complexity theory, this is not a fixed parameter tractable problem. If I fix the parameters, I mean, if I make even if I make the parameters very large, this thing remains somewhat tractable. I mean, it's only changing the constant factor in front. Here, it's changing the degree. If I make the parameters very bad, the runtime degrades in the degree of the polynomial bounding the runtime rather than the constant factor in front. So this is a question which is, so that has been studied for other kind of problems in complexity theory. But here the question is this just a matter of inadequacy of techniques, or are we just not analyzing correlation decay or these zero freeness based algorithms the right way? Or is there something more fundamental here about distinction between randomized and deterministic algorithm, that for these problems there is a separation between what the two can do? So I had a short write-up, informal write-up that I wrote a few years ago, describing the Liang theory for non-physicists. So if you're interested, you can.
Thank you. I'm here for a completely strange reason, which is that TIFR has a lovely collection of art. And Juneja thought that we should have a small piece on what paintings are there. Some of the paintings that I will show you are actually outside. Some are in director's office and stuff like that, so you can't access them. But we do have a beautiful collection of paintings in TIFR. So I'll just go run through that set. Basically, TIFR has, from the 60s and 70s, one of the largest collections of modern Indian painting. We have them from 50s to 70s. TIFR was a voracious collector of paintings. So we have some of the finest paintings of that time. 224 paintings is what we have. And we have some 30 sculptures, and I'll show you pictures of some of these. 4 of these are ancient archaeological monuments. That's part of the story. It largely consists, if you are an art historian, then it largely consists of what is called the third epoch of modern Indian painting that started soon after India's independence in 47. It is an interesting mix of trying to attempt to take Western art form and use it for Indian expression, but the artists were very keen that they should not overlap with tribal arts of India. So there is an interesting attempt to avoid tribal art, and there is an interesting attempt to create new art which is Indian. Our director Homi Bhabha was himself a great lover of art. In fact, He took a year off after his typos in Cambridge just to learn art and then went back to science again. An amateur artist himself, and I'll show you some of the impressions that he has left behind in art in TIFR. This is the only painting of his which we have in our collection. There are probably others, but we don't have them. It's a fairly large one, 100 centimeters or 1 meter by 1.3 meters long. It's a fairly large painting. And if you are, it was done way back in early 60s, but you can still see the idea of TIFR's corridor that comes from something like this. These are some of the sketches that we have from his collection, but that is about all that we have about his art. Now let me start with the TIFR collection itself. Okay, at the entrance of TIFR itself, there are two beautiful paintings. One of them is Kishan Khanna, and I'll discuss that in a minute, which is called The Dead and the Dying. And you would think that Dead and the Dying is not exactly the scheme you want to welcome people with into your institute, but it's still a magnificent piece of painting. It's huge. It is 2 meters by 1.5 meters. And as you enter, you can see it right in front. And the reason why this painting is beautiful is simply because, apart from the size of the canvas and the impression it leaves behind, is the fact that it uses no bright colors whatsoever. The only colors that are not dark are the white colors, and there are 7 people gambling over here, and there's a dead body at the back, the dead and the dying, and that's all that is there. But the sheer color contrast and the lack of it that he uses is something that makes it so fantastic. It's one of the few paintings of TIFR that have gone recently to USA and UK under this Government of India attempt to project Indian art. But this Kishan Khanna's 2 meter by 1.59 meters is something you enter with. The second one is a little more simple. It is the imposing mural that we have on the mezzanine floor. It was in order to select a good mural, Homi Baba invited a lot of suggestions, and all suggestions that were given were purchased by TIFR. So TIFR is the entire collection of all the possible ideas that came up for that mural of TIFR. And the interesting thing about these murals, and I'll show you all the examples, is that it gives you an idea about what the community thought of TIFR when TIFR started. What did it look like to the artist? And that's what we will do. This is the mural that I'm talking about, a fairly large piece. You can't see the whole of it simply because of the pillars and stuff. But the selection of mural itself is a fairly interesting proposition, because the shortlisted works are now part of TIFR's collection, and they're an interesting idea of what the artist thought TIFR would be like when TIFR started. So let me show you some examples. This is called Cosmos in the Making. Baba himself was an astronomer, and you can see there is a sun here, and there's this idea of wild creativity. And the colors are essentially colors of the sun because of the fact that Bendre was very fond of it. Again, it's a very large campus, 293, 3 meters wide and half a meter tall. All these are wide and tall simply because they were supposed to be on the mural. The second one, on the other hand, by Prabha, is called Black Moon, where she has this collection of creativities, but the moon is drawn black simply as a matter of contrast to the moon that we see. The third one is the only painting that we have which is in the conventional class of genuinely Indian tribal related paintings. It is called Krishna and Balram, and 3 of them face one side, 3 of them face the other side. Krishna and Balram are legendary brothers from Indian mythology, and various stories associated with it. But this is the only one that we have which is more in classical Indian painting style or tribal Indian painting style. Then we have Ara. Ara was our in-house artist until he was alive. He would come very often to TIFR. And his idea of TIFR's creation was that it should be celebrated as a spring festival. And you can see his ideas of spring festival. In India, spring festival is called Holi, where we sprinkle water and color. So you can see bits of those over here. But essentially, this was his idea. All these murals, by the way, are hanging somewhere in the institute. This Badri Narayan thought that because TIFR was connected with science and research, the tree of life is what will occupy TIFR. So he had this mixed media paper and art. Again, it's a fairly large one, half a meter by 3 meters, because that was the requirement of the painting, and you can see aspects of life. This, on the other hand, Satish Gujral thought we should worry about vigil to look after science and to look at science. Satish Gujral, of course, is the brother of I.K. Gujral, who became the Prime Minister of India at some stage. Again, 3 meters by half a meter. This is a picture called by Heber called Civilization, and this is interesting for a variety of reasons, because it shows the human evolution from early rock art drawings and fear of electricity to worship of gods and natures and the powers that be, to farming, eventually technological evolution, to the extent where we control the power of electricity that once scared us so much. So there's this path of civilization that Heber has drawn. Again, it's a 3 meter wide painting, and he thought this would be appropriate for something like TIFR. Man Triumphant is what Raval called his painting, where humans essentially control all nature, the moon and the sun and all the wild animals, etc., to their own likelihood, to their own liking, and for their own exploitation. The one that won is, of course, this one. Again, we have the original, and there's something interesting about the original. It is called Bharat Bhagya Vidhata. So it shows various aspects of Indian life. There is a great gate, there is an elephant over here, there is a horse here, and there are other human beings, there's a camel here, and the peoples and tribals of various decoration over here. So essentially, it was an idea that it would show the vibrancy of life in India, because various aspects of people of India were done there. Again, the original, of course, is 2 meters. The real one is 3 meters by 18 meters, done on the wall in 1963, and eventually Hussein in 2000 came personally and had the coloring pattern because it had gone faint. So that's the original date is 1963. The interesting thing is that even though Baba liked this painting, he didn't like the coloring of it. He thought it was not bright enough. It was a little too morbid with too many blues and dark colors. So the painting that finally went up is like this. It is much more red. It was much more vibrant. It has very few blues inside, and compared to what the original was, this is much more optimistic, and that's how it goes. So Baba had the audacity and the ability to tell Hussein that however good his painting was, this was not the colors he wanted. And Hussein is a very, very big name. By the time you talk of 63, he is one of the most expensive painters in Indian history. He recently passed away. So that is what it is. Then TIFR is a huge collection of some of the greatest names of artists from the 60s and 70s. And my suspicion is that TIFR's art collection is more expensive than rest of TIFR put together. That is the kind of art collection we have. Baba identified them very early, so we have